Now, there are many different types of memory for microcontrollers. So I refer to a few of these. Some are inside processors, as others are external to processor core. And by memory, I'm using the term loosely just because it's anything that can store or remember a value, even if it's temporary. Okay, so those of you who've taken processor organization, computer architecture know most processors have this thing called registers, right? Registers are inside CPU for holding kind of the scratch results. You adding two numbers, the result you put in the register because you couldn't use it again. So you tend to have about anywhere from 4 to 32 registers, and they are used directly by the processor, and they are accessed very quickly. Now, internal memory could be something that you you might not find on a lot of the regular general purpose processor, but you find more with embedded microcontrollers. And they're on the order of 128 to 256 words. And these are also close to the processor. And sometimes these are overlaid or they overlap registers. So maybe the first 8 of them are mapped to registers. This is actually pretty common. 8051 does this, AVR does this, maybe a few other architectures also do this. Um, Now, so internal memory, or some might call scratchpad memory, are found on some embedded processors too. So that's a much smaller amount of memory that the microcontroller can use just for quicker computation. Now, there's also memory that's external to the microprocessor core. And when you write programs, if there's a difference, then you may use a different keyword to say that's I data for internal data or X data for external data. But just because it's external to the core doesn't mean it's actually a separate chip, because now many things are integrated on the same chip. So it's external only to the core part of the microprocessor, but it could still be on chip. So and that's what we see a lot. So even the 8051 here, there is external data memory, but it's part of the same chip. It's on the same chip. It's just outside the core. External to the core doesn't mean external to the chip. Okay. Now there's different kinds of what's called external processor core memory. So they're roughly SRAM for data and flash for program or constant data. And then there's the off-chip memory. Okay, now that's really a separate component, or sometimes it could be stacked on. Okay, so that this is something you need to know when you try to take a look at some of the specifications for microcontrollers, because there's a wide variety. Now, so in terms of address spaces for code and data, there's these two classes, something called Princeton architecture and Harvard architecture. Princeton architecture is also called von Neumann architecture. That's probably what you have heard more. And von Neumann architecture means you put data and program in the same space. And there's really no inherent distinction between program and data. You can read program as data, you can write data and then run it as a program. Okay. Whereas Harvard architecture uses separate spaces for instruction and data. And you tend to see more Harvard architectures for microcontrollers. That's just because it's a little easier to design a system this way. But no, not always. So that's just a trend. But there are plenty of microcontrollers that follow Princeton architecture or von Neumann architecture. So most microcontrollers are Harvard architecture. So for example, 8051 clearly has separate spaces for code and data. And AVR, you may have from Atmel. That's another very popular microcontroller. Also, Harvard architecture. And in fact, you may have heard DSPs, digital signal processors. Many are also Harvard architecture. Now, whereas for von Neumann architectures, there's more flexibility. In fact, most of your general purpose computers, like Intel x86, most PCs, they tend to have what's called von Neumann architecture or Princeton architecture. That is same space for memory and for data memory and program memory. And this is more flexible. Why? Because you can do what's called self-modifying code. That is, your program can write a program for itself to run. It's like, wow, that's pretty cool, but kind of dangerous, isn't it? Yes. So don't try it unless you know what you're doing. And most operating systems will prevent you from doing that unless you really know what you're doing. Now, this is what's done a lot of times for bootloaders. A bootloader can modify its own memory, or sometimes you have an interpreter. Many of you may have heard of Java, right? Java is an interpreter, and sometimes to make an interpreter run fast is to use techniques that involve self-modifying code, or it may do just-in-time compilation. That is, it translates Java code to native code, and so that is what allows it to run faster. But that works only if you are allowed to write to memory that you can run. Okay. Now these architectures that are von Neumann. So ARM is one we saw, right? It's the same space, lower part for code, a little higher part for data. There's another family called MSP 430 from TI. That's also pretty popular microcontroller family, and that is von Neumann architecture as well. That's a 16-bit architecture. Now, if you have a Harvard architecture, you could actually make it or force it to be von Neumann architecture if you just wire up the memory together. Because what Harvard does is it generates space address to access data, generates separate address to do program code. But these are wires. If you wire them together and have ways for them to access separately rather than together, there's no conflict, and then you can actually convert a Harvard architecture into a von Neumann architecture. And some processors do that. So, for example, 8051, you could have ways to kind of force them to be the same space or overlapping space. That happens. Now, okay, so I mentioned the DSP a little bit. DSP stands for Digital Signal Processors. And this is another class of embedded processors, but they're more specialized for numeric operations. Sometimes the distinction between DSP and microcontrollers might not be so clear, but other times they're very clear. And usually you look for an instruction called multiply accumulate, or MAC, M-A-C. And if it has multiply accumulate instruction, or if it has instructions that operate on data arrays, that is, it's one instruction that works on a bunch of consecutive elements, or some kind of data banking, or what's called zero delay loop or hardware looping. That is, it's one instruction that just repeats without having to have a jump instruction. Then, yeah, chances are you're looking at a DSP. Now, DSP is used more for things like your audio codec, right? So MP3 player playing music, that's usually a little DSP there. Or it's doing compression, data handling, right? Image processing, maybe MPEG, JPEG, right? There's a lot of more specialized operations that use DSP. You could try to do this with a more general purpose microcontroller, but you might find it's really pushing its limit and it's not as power efficient. So for those more specialized cases, you might consider using a DSP instead. But we won't be using DSP in our course here. I think that because that involves digital signal processing algorithms that are beyond the scope of this course. But we'll look at microcontrollers. And once you know microcontrollers then, and you know the DSP algorithms, then I think it makes more sense to then use DSP. But before then, let's stick to microcontrollers. These are more general purpose, and they're good at control rather than a lot of intensive calculation.